Hello. In our last video, we started off by talking about how polymers have a molecular weight distribution. Not every chain is the same length, so not every chain has the same mass or molecular weight. And because of that, we learned how to calculate the average molecular weight, and we learned to do that in two different ways: the number average molecular weight and the weight average molecular weight. In this short video, we're going to focus on molecular weight distributions. But before we do that, let's look at these equations one more time. We've got our number average molecular weight equation here and our weight average down below. And the weight average always skews to a higher molecular weight. And one way to understand what those averages, like how those averages calculate different numbers, is with these two plots. Here we've plotted I've taken a perfect bell curve, and we've plotted the number of chains versus the mass of those chains, or the molecular weight of those chains, on the x-axis. And when we do that, the number average degree of polymerization is right at the center of that bell curve. And in this example, it's 150,000 grams per mole. If instead we plotted the mass of the chains instead of the number of the chains, you can see that this bell curve shifts. So it's a perfectly shaped bell curve, but now the center is at the weight average molecular weight. It's 156,000 grams per mole. So the red line in both of these plots is the same. We can see that we shift this curve to higher molecular weight when we plot the mass of the chains, or the weight fraction of the chains, as opposed to the number or the number fraction of chains. Now we want to focus on the molecular weight distribution. If we have an ideal polymer where every single chain is the same length and has the same mass, the molecular weight distribution would be a single spike, like it is for small molecules. A real polymer with a very narrow molecular weight distribution might look something like the curve in blue, where a real polymer with a broad molecular weight distribution, it's going to be much more spread out, like the curve in red, that bottom curve. All three of these curves happen to have the same number average molecular weight. Would they have the same weight average? No, because that distribution is different, and they have a different amount of higher molecular weight chains, so that weight average molecular weight is going to be different. In the idealized case, the number average and the weight average are equal because every chain is the same length, so those equations collapse into the same thing, right? It's not an average, it is the mass of all of the chains. Where for the red chain, you're going to have the highest weight average molecular weight because you have more. If we go back to our old example, you have more elephants. So it's going to skew to that higher molecular weight, as opposed to the narrower molecular weight. The weight average is going to be lower. It's going to be closer to the number average molecular weight. I also want to point out that you don't have to have something shaped sort of like a bell curve. It's totally possible to have a bimodal molecular weight distribution, a high molecular weight tail. There's lots of possibilities and lots of differences possible for the molecular weight distribution. It's something that has to be measured experimentally. So a big question is, how can we describe the breadth of the molecular weight distribution? And the way we do that is with what we call the polydispersity index. The polydispersity index, or the polydispersity, is just a ratio of MW over MN. So the weight average molecular weight over the number average molecular weight, that is always greater or equal to 1. Okay. If you ever calculate the polydispersity index and you get a number less than 1, you know you had to have made a mistake. And the most common mistake is that you put MN over MW. Polydispersity is always greater or equal to 1. Now think about it. What does a polydispersity index of 1 mean? It means that every single chain has the same mass. Okay, all the chains are the same length. That's the only way you get a polydispersity index of 1. So just remember that. Your polydispersity index, we're using this to measure the breadth of the molecular weight distribution. It's a super simple calculation, and it's just the ratio of the weight average molecular weight over the number average molecular weight. Thanks for watching this short video.